Hello student, I am Dr.A.K. Sinha, Professor of Chemistry. Today I am going to discuss chemical properties of group 2 elements, means alkaline earth metals. Okay, last class I discussed physical properties of group 2 elements. Now I am going to discuss chemical properties. The alkaline earth metals are less reactive than the alkali metals. This is first important point. Alkaline earth metals are less reactive than alkali metals. The reactivity of these elements increases on going down the group. First, I am talking about the reactivity towards air and water. Beryllium and magnesium are kinetically inert to oxygen and water because of the formation of an oxide film on their surface. However, powdered beryllium burns brilliantly on ignition in air to give beryllium oxide and beryllium nitride. Magnesium is more electropositive and burns with dazzling brilliance in air to give magnesium oxide and magnesium nitride. Calcium, strontium and barium are readily attacked by air to form the oxide and nitrides. They also react with water with increasing vigor even in cold to form hydroxides. A special reaction is for magnesium with oxygen and nitrogen. Magnesium forms magnesium oxide and it burns also dazzling brilliance. In air it burns magnesium and forms magnesium oxide, and magnesium forms magnesium nitride Mg3N2. Calcium, strontium and barium are readily attacked by air to form the oxide and nitride. Okay, calcium, strontium and barium. These three elements quickly attacked by air and forms oxides and also nitrides. They also react with water. These calcium, strontium and barium react with water with increasing vigor even to cold. In cold also it will react and it will form hydroxides. And for beryllium, already told you, beryllium forms beryllium oxide and also forms beryllium nitride. Okay, Be3N2. Now reactivity towards the halogens. All the alkaline earth metals combine with halogen at elevated temperature, forming their halides. M plus X2. M is capital M, general metal. M means metal. M plus X2. X is halogen, maybe fluorine, chlorine, bromine, iodine. Then M plus X2, it forms MX2. Okay, here X is equal to fluoride, chloride, bromide, iodide. Thermal decomposition of ammonium beryllium fluoride NH4 BeF4. Okay, this compound is important. NH4 means ammonium Be beryllium F4 means fluorine. Then ammonium beryllium fluoride is the best route for the preparation of BeF2. How you will get beryllium fluoride? Then you can get it from ammonium beryllium fluoride. Okay, and beryllium chloride is conventionally made from oxide. Okay, beryllium chloride, how will you get? From beryllium oxide, BeO plus C plus Cl2. You will get beryllium chloride plus carbon monoxide. Again I am telling you, beryllium oxide plus carbon plus chlorine gas. Okay, temperature you have to maintain around 600 to 800 Kelvin. Then you will get beryllium chloride plus carbon monoxide. Third reaction, reactivity towards hydrogen. Okay, all the elements except beryllium combine with hydrogen. Okay, except beryllium, all will combine with hydrogen upon heating to form their hydrides. Hydrides means MH2, metal hydride, like beryllium hydride, BeH2, beryllium hydride. However, this can be prepared by the reaction of beryllium chloride with lithium aluminum hydride. Okay, I told you except beryllium, all metals, all elements except beryllium of this group combine with hydrogen upon heating to form their hydride, metal hydride. What about the beryllium? BeH2, beryllium hydride, however can be prepared by the reaction of beryllium chloride with lithium aluminum hydride. Reaction you can understand, beryllium chloride plus lithium aluminum hydride. Balanced equation 2BeCl2 plus lithium aluminum hydride LiAlH4. It gives 2BeH2 plus LiCl plus AlCl3. This reaction is very, very important. Again I am telling you, 2BeCl2 plus LiAlH4, lithium aluminum hydride. It forms 2BeH2 plus LiCl plus AlCl3, aluminum chloride. Then this way you will get beryllium hydride. Fourth reaction, first reaction I told you towards with air and water. Second I told with halogen. Third I told with hydration. Third I told with hydrogen. And fourth I am going to tell, that is about reactivity towards acids. The alkaline earth metals readily react with acids, liberating dihydrogen, means hydrogen gas. M plus 2HCl, M means metal, M plus 2HCl, it forms MCl2 plus H2. Maybe magnesium chloride, calcium chloride, barium chloride, etc. Next reaction I am telling you, reducing nature. Like alkali metals, the alkaline earth metals are strong reducing agents. This is indicated by a large negative value of their reduction potential. Already I have discussed. Okay, these alkaline earth metals are a strong reducing agent. However, their reducing power is less than those of their corresponding alkali metals. Alkali metals are stronger than alkaline earth metal. Okay, in reducing nature, means reduction potential, alkali metals have more than alkaline earth metal. Okay, beryllium has less negative value compared in group 2. Beryllium has less negative value compared to other alkaline earth metals. However, its reducing nature is due to large hydration energy. Here, this reducing nature is due to large hydration energy associated with the small size of beryllium. Okay, and I just especially I told about the beryllium. Beryllium has a less negative value compared to the other alkaline earth metals. Then less negative values I told you about the beryllium. However, the reducing power is due to, or reducing nature is due to large hydration energy associated with the small size of beryllium ion, and a relatively large value of the atomization enthalpy of the metal. Now, next reaction is with solution in liquid ammonia. Solution in liquid ammonia. Like alkali metals, the alkaline earth metals dissolves in liquid ammonia to give a deep blue black solution, forming ammoniated ions. In alkali metal it was blue, deep blue, but here you will get deep blue black solution forming ammoniated ions, and its reaction is same way, M plus X plus Y NH3. There also same thing was there. Ammonia was there, NH3. Here we are adding M. This M, there also metal was reacting, here also metal is reacting. Then metal plus X plus Y NH3, it is giving two product of ammonia. First product is MNH3 whole X. Same reaction what was with alkali metal, here also MNH3 whole X. It is a complex ion, outside 2 plus is there. And other complex of ammonia is there, ENH3 whole Y. It is also complex, and outside negative ion is there, one negative ion. Then here you will get these things, ammoniated ions. Ammoniated ions you are getting two types. One positive, that is MNH3 whole X, and outside, because it is a complex ion, it is a cation, 2 plus charge is there. And another product is, that is a ENH3 whole Y. Then it will form two molecules, 2ENH3 whole Y, and outside 1 minus. It is the anion. Then I told you that this ENH3 to ENH3 whole Y power 1 minus. This is actually its color is blue black. Okay. Now from this solution, then ammoniates means MNH3 whole 6 2 plus can be recovered. MNH3 whole X 2 plus. Okay. But here x in particular, when x value is 6, then it will form MnS3 whole 6 and power is 2 plus cation. It is cation, complex ion. Okay, outside 2 power is there. Then this can be recovered. Now come to the usage application. Beryllium is used in manufacture of alloys. As for example, copper beryllium alloy. Okay, copper beryllium alloy. It forms a copper beryllium alloy. Okay. Then copper beryllium alloy are used in the preparation of high strength springs. It is used in forming the springs. Okay, high strength spring. Now another use, metallic beryllium is used for making windows of X-ray tube. Okay, and for magnesium, use of magnesium, magnesium forms alloys with aluminum, and zinc and manganese, and tin, all three, zinc, manganese and tin. Zinc, I am talking about magnesium forms alloys with aluminum. Okay, it also forms alloys with zinc, and it also forms you can say alloys with manganese and tin. Means magnesium forms alloys with aluminum, with zinc, with manganese and with tin. Magnesium aluminum alloys being light in mass, it is very light. Okay, magnesium aluminum alloys being light in mass are used in aircraft construction, aeroplane, aircraft construction. This is used because it is lightweight, it can fly easily, it is not heavy. Okay, metal is, this alloy is very strong, and this is lightweight. Magnesium powder, I am talking about magnesium powder and ribbon, also you can tell magnesium ribbon or magnesium powder is used in flash powders and bulbs. In bulbs also it is used. Okay, in incendiary bombs, bomb also in that it is used, incendiary bombs and signals. It is not atom bomb and hydrogen bomb. It is just like a bomb, incendiary bombs and signals it is used. It is used in where magnesium powder or ribbon I am talking is used in flash powders and bulbs. Okay, incendiary bombs and signals. A suspension of magnesium hydroxide in water, that is called milk of magnesia. A suspension of magnesium hydroxide MgOH2 in water, if you will dissolve MgOH2 in water, then this is called milk of magnesia and is used as a antacid, antacid in medicine. Magnesium carbonate is an ingredient of toothpaste. We are paste we are using, toothpaste. In that also magnesium carbonate is present. Calcium carbonate is also present. Magnesium carbonate is also present. The magnesium carbonate is an ingredient of toothpaste. Calcium is used in the extraction of metals. Now use of calcium. Calcium is used in the extraction of metals from oxides which are difficult to reduce with carbon. Calcium I am talking about. Calcium is used in the extraction of metals, okay, from oxides, means calcium oxide, any other oxides are there, and you want metal of that metal, pure metal, then calcium is used there. Calcium is used in the extraction of metals from oxides which are difficult to reduce with carbon. Generally with it is carbon is used for extraction of metal, but when carbon fails, here carbon fails, it is difficult with carbon, then calcium is used here, okay. Calcium is used here in the extraction of metals from oxide which are difficult to reduce with carbon, okay. Now again further we can see calcium and barium metals, owing to their reactivity with oxygen and nitrogen at elevated temperature, have often used to remove air from vacuum tube, okay. Actually you have to remove air in vacuum, then calcium and barium metals are used. Calcium and barium metals, owing to their reactivity with oxygen and nitrogen, it reacts fast with oxygen and nitrogen, calcium and barium. That's why particularly, but this is done at high temperature, elevated temperature. That's why often it is used to remove air from vacuum tubes. Radium salts, now come to the radium. Radium salts are used in radiotherapy, for example in treatment of cancer. It is very very important use of radium. Radium salts are used in radiotherapy, for example in the treatment of cancer. Then now I have told you uses of that group second metals, that is alkaline earth metals. Now I am going to discuss general characteristics of compounds of the alkaline earth metals. Okay, these things. The dye-positive oxidation state of metal ion, M2 plus. Okay, the dye-positive oxidation state, that is the M2 plus, is the predominant valence of group 2 elements, means plus 2. The alkaline earth metals form compounds which are predominantly ionic but less ionic than corresponding compounds of alkali metals. Alkali metals are more ionic than alkaline, okay. This is due to increased nuclear charge and a smaller size. You know that group 2 metals are smaller in size in comparison to the alkali. Then this, while less you can say this ionic, less ionic, then this is due to the increased nuclear charge and a smaller size. The oxides and other compounds of beryllium, and magnesium are more covalent. Here you should know oxides and other compounds. The oxides and other compounds of beryllium and magnesium are more covalent than those formed by the heavier and large-sized members. As for example, calcium, strontium, barium. These are comparatively in a group bigger than beryllium and magnesium. Beryllium magnesiums are more covalent than calcium, strontium, barium. Actually, in during bond formation, it will be not 100% ionic. some percentage of covalent will be also there. Maybe 80%, 20%, 90%, 10%, 10% covalent, 90% ionic. Okay, that's why this bond depends percentage of covalent character, percentage of ionic character. That is correct. Not 100% you can tell ionic, but ionic percentage may be more, covalent percentage may be less. Here beryllium and magnesium are more covalent in comparison to the calcium, strontium and barium. They are more ionic. Calcium, strontium, barium are more ionic than beryllium and magnesium. Or you can tell beryllium, magnesiums are more covalent than calcium, strontium, barium. Okay, in bond actually it happens like this only. Okay, HCl, it is not you can say ionic 100%. It is around 80%. It is ionic, and 20% around that is covalent character. Both character will be found. But because when percentage of ionic character is more, then it is called ionic. And if covalent character is more, then it is called covalent. But generally in ionic character, this ionic bond, ionic character will be more, maybe 80-85%. More than that also, covalent character will be less. But in covalent bond, covalent character will be 80-85%. Ionic character will be very less. That's why it is called polar. Polar means less charge, less positive, less negative. Then now I am going to tell more this about oxides and hydroxides. Its characteristics. Oxides and hydroxides of alkaline earth metals. General characteristics I am telling you. The alkaline earth metals burn in oxygen to form the monoxide like MO, metal oxide. M means metal oxide, which except for beryllium oxide have rock salt structure. Exception is beryllium oxide. Beryllium oxide is not the rock salt structure, but other metals have rock salt structure. The beryllium oxide BeO is essentially covalent in nature. The enthalpies of formation of these oxides are quite high, and consequently they are very stable to heat. Okay, any molecule whose enthalpy of formation is high, and they will be, you can say, they have less effect of heat. The enthalpies of formation of these oxides are quite high, and consequently they are very stable to heat. Okay, particularly I am talking about here beryllium oxide. The beryllium oxide is essentially covalent in nature. Okay, the enthalpies of formation of these oxides are high, and consequently they are very stable to heat. Beryllium oxide is amphoteric, while amphoteric means it can behave as acid as well as base. BeO is amphoteric, while oxides of other elements are ionic in nature. All these oxides except beryllium oxides are basic in nature. Beryllium oxide have both character, but all the other oxides except BeO are basic in nature and react with water to form sparingly soluble hydroxide. Sparingly soluble means very less soluble. Okay, then they form a sparingly soluble hydroxide, means MO. M is metal. Okay, metal, M means metal. Then MO means metal oxide plus H2O, it will form MOH whole 2, metal hydroxide, like calcium hydroxide, CaOH whole 2, MgOH whole 2, SrOH whole 2, BaOH whole 2, etc. Okay, the solubility, thermal stability, and the basic character of these hydroxide increase with increasing atomic number from magnesium hydroxide to barium hydroxide. Solubility also increases, thermal stability also increases, means no heat effect of heat is very less. Okay, then solubility increases, thermal stability means in the presence of heat also it will be stable. Then the solubility also increases, thermal stability also increases, and the basic character also increases. Basic character of this hydroxides increase with increasing atomic number from magnesium hydroxide to barium hydroxide. Okay, the alkaline earth metal hydroxides are however less basic and less stable than alkali metal hydroxides. Okay, alkali metals are more you can say this stable. The alkaline earth metal hydroxides are less basic and less stable than alkali metal hydroxides. Beryllium hydroxide is amphoteric in nature as it reacts with acid and alkali both. Example I am telling you, beryllium hydroxide means BeOH whole 2. It reacts with base. BeOH whole 2 reacts with base and it forms berylate ion. Berylate ion, BeRyLLate, berylate ion, BeOH whole 4, BeOH whole 4, 2 minus, berylate ion. Okay, now beryllium hydroxide is reacting with hydroxide. See here, beryllium hydroxide is reacting with hydroxide and it is forming berylate ion. Then you see its acidic nature. Now basic nature you can see, BeOH whole 2 reacts with now HCl. HCl means it is a basic nature, and first it reacted with OH, it means it was acidic nature. Then BeOH whole 2 plus 2 HCl plus 2 H2O, it forms BeOH whole 4, berylate chloride, BeOH whole 4 Cl2. This reaction is both reactions are very important. BeOH whole 2 plus 2 HCl plus 2 H2O, it forms BeOH whole 4 Cl2, berylate chloride. Okay, now I am going to tell about halides of alkaline earth metal. Halides, except for beryllium halides, all other halides of alkaline earth metals are ionic in nature. Beryllium halide is not the ionic. Okay, beryllium halides are essentially covalent and soluble in organic solvent. Because covalent is there, then obviously it will be soluble in organic solvent. It is soluble. Then beryllium chloride BeCl2 has a chain structure in solid state. It is found in solid state. Then it is in a chain structure. Means BeCl2, again another BeCl2, and again another BeCl2, then BeCl2, 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 like that way all BeCl2 are joined to each other. As for example, just like consider beryllium 4 valency you consider, then Be, two valency is you can say opened, and another two BeCl2, Be joined with 2 Cl, it is formed BeCl2. Now this Cl, these 2 Cl again it is joined with another BeCl2, another BeCl2 is there. From that these Cl, both Cl will join to that beryllium. Okay, then now again this second BeCl2 will join with third BeCl2, okay, means Cl2 will be in the middle between the two beryllium. BeCl, okay, both BeCl that will be in the middle of 2 BeCl2. Then Cl2 is in the middle, just like a chain. One side it is joining with one beryllium, and other side another beryllium. Actually chloride ion has only one valency, Cl1 minus, but here it is showing two bond, but this bond is not a strong. Okay, just it is simply it is making weak bond with other beryllium. And second chloride ion also same way, one side one beryllium joining, other side other beryllium is joining, but one side it is a strong, but another side it is weak. Okay, when chlorine is making double bond, it has no capacity to form double bond, but it is forming. Then one bond is weak, and it's you can understand this is just also you can tell electron will be only one electron is there with chlorine, but both side it is seeing with sometime it will live with beryllium, one beryllium, other time it will live with the another beryllium. 50% time it is spending. One electron sometimes it will go to the one beryllium, other time 50% it will spend with other beryllium. That's why it is making two bond. And boron hydride BH3, that is the B2H6, boron, that is a banana type of a structure is there, banana type of a structure. There also one electron bond is there, and situation is similar. Electrons are moving. Here also electrons are moving. Then like that way they will make a chain, beryllium chloride plus beryllium chloride plus beryllium chloride. Like that way all beryllium chlorides are joined to each other by chlorine atoms. Two chlorine atoms will be in the middle. Okay, and from the one chlorine atom will join both beryllium. Okay, and another chlorine is also there, BeCl2. Then BeCl2, the one Cl is joining with 2 beryllium, and another chlorine is also joining with these two only beryllium. Then now you can tell that two chlorine is joining with two beryllium. 2 chlorine is joining with 2 beryllium. Okay, in the chain reaction. BeCl again Be. Okay, just like little V shaped Be, and then upside, little upside Cl is there. Again Cl is coming little down, making bond with B, because B is in the just a straight line, but Cl is up. One Cl is up, other Cl is little down, little up, little down. Okay, it is making just like a parallelogram. Okay, and it is linking with all beryllium, all 4, 5, 6, whatever be 2 chlorines are there and 2 berylliums are there, it will make just like a parallelogram. Okay, then structure will be like that. All BeCl2, 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 BeCl2 all are joined to each other and making just like a parallelogram. Okay, then this is called chain. Okay, beryllium chloride has a chain structure in the solid state. Question is asked, chain structure. Now in the vapor phase, it is in solid phase, I told you. In the vapor phase, BeCl2 tends to form a chloro-bridged dimer. There only 2 BeCl2 will join and it will form dimer known as chloro-bridged dimer. Here it is called bridged dimer, chloro-bridged dimer, which dissociates into their linear monomer, means they can break and it form linear monomer, single BeCl2 at high temperature at the order of 1200 Kelvin. At 1200 Kelvin, this vapor phase BeCl2 will break into monomer. The tendency to form halide hydrates gradually decreases. For example, magnesium chloride MgCl2 8H2O, okay, calcium chloride 6H2O, strontium chloride 6H2O. See, it was in the beginning, it was with magnesium, it was 8H2O, MgCl2 8H2O, and in calcium it became calcium chloride 6H2O. Strontium also, strontium chloride 6H2O, and barium chloride 2H2O. It is decreasing down the group. The dehydration of hydrated chlorides. Now again you can see the dehydration of hydrated chlorides, bromides and iodides of calcium, strontium and barium can be achieved on heating. Okay, if you will heat, then this water will, which now it is absorbed, now 8H2O, 6H2O, 2H2O, they will lose the water molecules. The dehydration of hydrated chlorides, bromides and iodides of calcium, strontium and barium can be achieved by heating. However, the corresponding hydrated halides of beryllium and magnesium on heating suffers hydrolysis. Beryllium magnesium is an exception. It will suffer hydrolysis. The fluorides are relatively less soluble. Fluoride, okay, the fluoride of alkaline earth metals are relatively less soluble than the chlorides owing to their high lattice energy. Okay, fluorides are relatively less soluble in water than chloride. Reason is owing to their high lattice energy. Okay. Salts of, now I am telling you salts of oxo acids. As for example, it forms carbonate, it forms sulfates, it forms nitrates. Okay, three type of salts it will form. Then carbonate of alkaline earth metals are insoluble in water. Carbonate are never it will dissolve. It is very strong. Carbonates of alkaline earth metals are insoluble in water and can be participate not this thing precipitated can be precipitated by addition of sodium or ammonium carbonate solution to a solution of soluble of these metals. Then you listen. Carbonates of alkaline earth metals are insoluble in water and can be precipitated by addition, means if you will add sodium or ammonium carbonate solution, if you will add, then it will precipitate. Okay, by addition of sodium or ammonium carbonate solution to a solution of soluble salts of these metals. Suppose these metal salts are there, soluble salts are there, then if you add sodium or ammonium carbonate, then it will precipitate. Okay. The solubility of carbonates in water decreases as the atomic number of metal ion increases. Okay. As we will go down, the solubility of carbonate in water decreases as the atomic number of the metal ion increases. Okay, all the carbonate decomposes on heating. All the carbonates decomposes on heating to give carbon dioxide and oxide. After heating, that it will break into two parts, carbon dioxide and metal oxide. Beryllium carbonate is unstable and can be kept only in the beryllium carbonate is unstable and can be kept only in the atmospheric you can this in the presence of carbon dioxide you can keep it. Beryllium carbonate is unstable and can be kept only in the atmosphere of carbon dioxide, means in the presence of carbon dioxide only that you can say that can be kept, means beryllium carbonate, okay, is very unstable and can be kept only in the atmosphere of carbon dioxide. The thermal stability increases with increasing cationic size. It means I am talking about all carbonate of alkaline earth metal. Okay, thermal stability increases with increasing at cationic size. Means as we will go down in the group, then thermal stability increases. All carbonates of alkaline earth metals. Okay, now I am talking about you can say alkaline metals sulfonate. In common way, sulfates of alkaline earth metals. Now I am telling you, the sulfates of the alkaline earth metals are all white solid, white color, and stable to heat. They are strong, it will not break. Beryllium sulfate and magnesium sulfates are readily soluble in water. Okay, quickly it will dissolve. The solubility decreases. From calcium sulfate to beryllium sulfate. Okay, down. Solubility in water decreases. Calcium sulfate is less soluble, and barium sulfate is again very, very less soluble. Okay. Then strontium sulfate is also less soluble. Then calcium sulfate to beryllium sulfate, this decreases, solubility decreases. The greater hydrogen enthalpy of beryllium ion and magnesium ions overcome the lattice enthalpy factor, and therefore their sulfates are soluble in water. Means these beryllium and magnesium both are soluble, but calcium, strontium, barium sulfate are not soluble. Okay, this question is asked. then the greater hydration enthalpy of beryllium ion and magnesium ions overcome the lattice enthalpy factor, and therefore their sulfates are soluble in water, because hydration enthalpy are more for beryllium and magnesium. That's why it is soluble, overcome the lattice enthalpy. Now just come to the nitrate of alkaline earth metals. The nitrates are made by dissolution of the carbonates in dilute nitric acid. Any carbonate you have taken, alkaline earth metals, group 2 metals carbonate you have taken, I want nitrate, then these carbonate you dissolve in nitric acid, metal carbonate you dissolve in nitric acid, then it will form nitrates. Magnesium nitrate crystallizes out. This magnesium nitrate crystallizes out with 6 molecules of water. It will associate with 6 molecules of water. Mg nitrate, magnesium nitrate 6H2O. Magnesium nitrate crystallizes with 6 molecules of water, whereas barium nitrate crystallizes as the anhydrous salt, no water. Question is asked. Magnesium nitrate is associated with 6 H2O, but barium nitrate no H2O, only barium nitrate, no water. This again shows a decreasing tendency to form hydrates with increasing size. Okay, and with increasing size and decreasing hydration enthalpy, because as we will go down, then hydration energy will decreasing hydration enthalpy. That's why you can say this decreasing tendency to form hydrate. It will not form hydrate. Okay, this decreasing tendency to form hydrates with increasing size and decreasing hydration enthalpy. All of them decompose on heating to give an oxide like lithium nitrate. Okay, this nitrate will decompose. As for example, metal nitrate, balanced equation I am telling you, 2MnO3 whole 2. MnO3 is whole 2, metal nitrate, 2 molecules. 2MnO3, it will decompose and it will give 2MO, 2 metal oxide plus 4NO2, nitrogen dioxide, brown gas. Okay, brown gas plus oxygen. Okay, 2 gas it is giving. When metal nitrate will break, it will give NO2 also, O2 also, and oxide it will give. That is the main product. Then 2MnO3 whole 2, it gives 2MO plus 4NO2 plus O2, where M is equal to beryllium, magnesium, calcium, strontium, barium, etc. Okay. Then this I have told you about the these things, properties. Okay, chemical properties already I told you, uses also I told you, and general characteristics I told you. General characteristics of alkaline earth metal. Okay, that is as oxides and hydroxide. General characteristics of oxide and hydroxide I told you. Halide I told you. Salts of oxo acids, that also I told you. Means carbonate, about the carbonate I told you. About the sulfonates I told you. About nitrates I told you. Now I am stopping only here. Next class I will discuss 1-2 problem I will tell, and I will discuss anomalous behavior of beryllium, and also I will discuss diagonal relationship between beryllium and aluminum. Both are very important. Okay. Thank you.